One method for approximating the area of a region under a curve is by using rectangles. So let's say here is our graph. We can see that it's bounded between the points A and B, and we have a vertical line at x equals A, a vertical line at x equals B, and then there is our function. Okay, one way of determining the area under the curve is by using left endpoints. So that means you're making these rectangles where the area of the region outside the rectangle. So here we're creating these left endpoints. Okay, so the endpoints are on the left. Now we can also use what we call right endpoints. So the right endpoints, you can see here, is a little bit above the curve. So again, this is an approximation. So the area of the rectangles are outside the region. Okay, and then there's the midpoint rule. So here you can see that we have the midpoint. So the area outside the region, and there's the area outside the rectangles. So therefore, these are three different versions of being able to find the area under a curve. So let's first take a look at an example. Okay, let's say if we had the function negative x squared plus 5. Okay, so what that means is we're going to have a parabola that opens downward. So here we have 1, 2, 3, 4, and then 5. So here at the value of 5, we know that we're going to have a curve. It's going to go downward. So let's go ahead and draw that curve. Okay, so let's say that's the parabola. Okay, and then what we're going to do is we're just going to say that it's bounded by the vertical line at x is equal to 0, and it's also bounded by the line y is equal to 0. We want to find the area that's inside of this graph. Okay, and the next thing that we want to do is we want to determine these increments. So we have increments, let's say this is 2, this is 4, 6, 8, and then it ends at 10. Okay, so what we're going to do is we want to create some rectangles like you saw earlier here. So at the increment of 2, we're going to draw a rectangle. Okay, and then at 4, we're going to draw another rectangle. And then at 6, we draw another rectangle. At 8, there's another rectangle. And then at 10, we can see that we have our final rectangle. So you can see that in the area, and I'm going to draw this in the gray area here. Okay, this represents the error that we were talking about here. Okay. So the rectangle that we write in blue is using the right endpoints. So currently we're using the right endpoints. Okay, now if we wanted to, we could determine this by using left endpoints. Okay, and if we wanted to do that by using left endpoints, then we would start here. Okay, and then we would have the area that's outside of this rectangle. So here's our left endpoint. And then we have another left endpoint, another left endpoint, and then another left endpoint. So therefore, this would represent the left endpoints. Okay? So, what did we do so far? Well, what we've done, okay, is that we've created 5 rectangles. Okay, and now we want to be able to find the ratio of the total lengths to the number of rectangles. So we take the total length which is the increments, and divide it by the number of rectangles. Okay, so what is the total length of each rectangle? Well, it's in increments of 2, so we know that the total length for each rectangle is going to be 2. And how many rectangles do we have? Well, we have 5. So that means that this becomes 2 over 5, 4 over 5, 6 over 5, 8 over 5, and then 10 over 5. Okay, and so now what we want to do is we want to be able to find the area of each rectangle. So if we want to find the area of the rectangles, then we would do the following. Okay, we would take L1 and multiply it by the total length divided by the number of rectangles, which is 2/5, plus, okay, we have L2, and we want to multiply that by 2/5, plus dot, 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 plus the 5th rectangle times 2/5. Okay, so what does that mean? Well, that means that L1, okay, is going to represent the function. Okay, so that means that we have the function with an input of 2/5 times the value of 2/5 plus we take f of, now since this is 2/5, the next one is going to be 4/5. So it's going to be f of 4/5 times 2/5. And then plus, we have f, and this length is 6/5. And again, we're multiplying that by 2/5. Plus the next length, f of 8/5, and then multiplying that by 2/5, plus, and then the last one, we take f of 10/5, and then we're going to multiply that by 2/5. Okay? So again, this is what that represents. All right, so now that we have that, then we need to find out, we're going to plug 2/5 into the function. So we're going to put in 2/5 for x, square it, multiply a negative, and then add 5. So what that means is we do the following. So we're going to take f of 2/5, and then we plug it in for x, so negative 2/5 squared, and then we're going to add 5. Okay, so let me go ahead and do this here on the side here. So there's our first one, and then we want to find f of 4/5, which is equal to negative 4/5 squared plus 5, f of 6/5, which is negative 6/5 squared plus 5, and f of 8/5, which is negative 8/5 squared plus 5. And the last one is f of 10/5, which is equal to negative 10/5 squared plus 5. So plugging those into our calculator, rounding it to 2 decimal places, we get 4.84, 4.36, 3.56, 2.44, and then 1. So now what happens is we're going to get the value of f of that following, And so now what we're going to do is we're going to take that 4.84 and multiply it by 2/5 plus 4.36 and multiply that by 2/5 plus 3.56 and multiply that by 2/5 plus 2.44 times 2/5 plus 1 times 2/5. And so therefore that gives us the value of the following, 6.48. Okay, so what does 6.48 then represent? Well, what it represents is the following. It's going to represent the area or the approximating area that is underneath here that's in the blue, right? So that is an approximation. Okay, now again, we have that error that's in here, but this is an approximating area. So the approximating area that's under the right endpoints rectangle is 6.48.